After you've been studying science for a little while, you start noticing an interesting coincidence that keeps cropping up. For example, if you have an object moving at constant acceleration a for a time t and you want to figure out how far it went, the formula for that turns out to be s equals 1/2 at squared. For another example, if you had a spring that was displaced a distance x from its equilibrium with spring constant k, the energy of that spring turns out to be E equals 1/2 kx squared. And if you have an object of mass m traveling with velocity v, the kinetic energy of that mass turns out to be T equals 1/2 mv squared. So we have S equals 1/2 at squared, E equals 1/2 kx squared, T equals 1/2 mv squared. Why do so many formulas with that pattern keep coming up? Is it a coincidence? No, it's actually a calculus theme. Each of the examples are calculated from integration under linear function. The position is the integral of the velocity versus time, where the velocity is changing linearly with time. The spring kinetic energy is the integral of the force with respect to displacement, where Hooke's law says the force increases linearly. And the kinetic energy can be taken as the power integrated over time for an object with constant acceleration up to a velocity v. There are lots more examples as well, and here's a really interesting one you may not have thought of before. The simplest way to compute the area of a circle is to divide it into rings like this, where you have an infinitesimal thickness of the ring, and you fill the circle with rings like that. Each area of the ring is dA equals the circumference of the ring times the thickness of the ring, dr0. And the reason this falls under the same category is that the circumference increases linearly with the radius r0. Actually, this coefficient 2 pi is a little bit annoying because it has this factor of 2 in it, and that will get rid of the 1/2. So let's instead call it tau times r0, where tau is defined as 2 pi. So now the circumference increases linearly with the radius, and when we integrate to find the area of a circle, we find the normal, usual formula for the area of a circle, A equals 1/2 tau r squared. And listen, do get used to thinking in terms of tau, because if you get hung up on pi, that is not going to make you popular. And just in case you don't really believe this demonstration, let me show you a film of me actually deconstructing a circle in this way. I take it and break it up into individual rings. Each ring turns out to be a size that is a linear function of how far it is from the center of the circle. So when I add up all the areas, it turns out I have a triangle, and you can easily see that the area of a circle is 1/2 tau r squared. So the origin of all of these formulas with this form is the fact that the integral from 0 to x of mx0 dx0 is 1/2 mx squared. In other words, it's the power rule. It's this factor of x squared over 2 that comes from the power rule run in reverse. And I will mention in passing that if you try to find the volume of a cone, then you're going to be adding up disks that are proportional to the square of their distance from the vertex. So the power rule gives you this factor of 1/3 instead of 1/2, and that's why you see a 1/3 in certain volume formulas. So if you are given a problem, an application problem in integrals that looks something like this question, find the area of this triangle, just remember that there's a difficult way to do it, and there's an easy way to do it. The difficult way would be to find the equation for that line and then integrate that line with respect to x. The easy way to do it would be to make up a nice new coordinate system, say u, and you can see that the function is linearly increasing from 0 as a function of u. The formula for that is going to be y equals h over b times u, and when you integrate that from 0 to b, then you could see in your mind's eye the answer is going to be u squared over 2, and the area is going to turn out to be 1/2 base times height. So do it the easy way instead of the difficult way, and notice this pattern when it comes up.